Thank you. Thank you. Can you hear me? Okay, so I'll talk about Android wireless communication without internet today. Hi, my name is Fumi. I'm a software engineer at Microsoft, not working on Android, but on robotics right now. So please keep in mind that today's talk has nothing to do with my company, but it's a result of my hobby. Okay, here's the agenda for today. First, I will briefly describe the wireless communications without internet, typically available on Android. I will then show you how to use them in Android by showing you the code. In doing so, I try to include as many of the insights I learned while writing the code as possible. I then give my thoughts on which of these wireless communications would be appropriate to use in what situations. Finally, I will conclude with some interesting related topic that I was not able to dive deep today. Let's get started. All right. Now, what are the typical wireless communications without internet available for Android? Amazingly, any devices you can buy for $100 often has most of the features listed here. That is, Bluetooth, Wi-Fi, and BLE nowadays, as well as NFC. Let's look at them in order. Okay, Bluetooth. When it comes to wireless communication around us, Bluetooth is probably at the top of the list. Bluetooth 4.0 has recently been introduced, which is called Bluetooth Low Energy. So the previous Bluetooth is specifically referred to as Bluetooth Classic. It utilizes 2.4 gigahertz band and 79 channels of frequency hopping spread, making it congestion resistant. Even today, it is used very frequently with devices like earphones and keyboards. Now let's look at Wi-Fi. Wi-Fi is as essential to our mobile lives as Bluetooth. We usually connect to a Wi-Fi access point to enjoy high-speed network. However, connecting to an access point is not the only way to use Wi-Fi. In fact, Wi-Fi can be used for P2P or directly connected by several people in close range to form an ad hoc network. I will be speaking about this today. And last but not least, recently, Bluetooth Low Energy, or simply BLE, has become available as a power-efficient Bluetooth. Although the name says Bluetooth, classic Bluetooth and BLE are not really compatible. I think I can have an interesting talk about this as well today. Oops, I forgot about NFC. NFC, Near Field Communication, is a very interesting technology. In fact, NFC is used in smart wallets and other applications, like, my number, right? As the name suggests, this is definitely another form of short-range wireless communication. But since this is a very short distance, like less than 4 centimeters, I have not included it in today's talk. Now that we know what technology I will cover today, let's see what kind of code we can actually write to use them in Android. First of all, let me say that there will be a lot of source code on this slide today. You will probably get tired of it along the way. Here is the complete source code. You do not need to understand everything during this talk at all. Just pay attention to the really main point and listen to the, please refer to this slide and just focus on the main point during my talk. Okay, Wi-Fi Direct. There's good reason to start here. Wi-Fi is the closest link to internet programming that you are used to. Simply put, Wi-Fi Direct is Wi-Fi without an access point. Once you establish a connection with someone nearby, the rest is complete TCP socket programming. Okay, let's look at the actual code. First, declare permissions. This is as shown on the official site. Don't worry about it. You don't have to memorize it. Now, we will get the Wi-Fi P2P manager and channel we will use to connect over Wi-Fi. What we will do now is to find peers to connect to. To do this, we need an intent filter and a broadcast receiver in case there is a change in peers. This is broadcast receiver. Each callback should be implemented later, so don't worry about that. The broadcast receiver and the intent filter should be tied to the lifecycle with on resume, and on pause, as you would normally do. Now that we are ready, let's use discover peers to find peers around us. There are a couple of things to note. First, Wi-Fi Direct does not separate advertisement and scan or discover, which means people who want to connect need call discover peers to each other. Only when both parties find the other can a connection be made. Now, implement the broadcast receiver callback. That was left blank earlier. What you receive here is peer changed action. Since there has been change in peers, use request peers to get a list of peers around you. Keep the list you have acquired so that you can connect to it at any time. So this is the peers around you, right? Now, connect to the other party from the found list. Since we already have the peer device information in the list, let's connect with connect method with using it. If there is change in connection status, connection changed action is called back. Once isConnect method confirms that the connection has been made, request connection info should be called to obtain the details of the networks. Excuse me. All right. The Wi-Fi P2P info passed to the callback is used to branch the process. If they connect to you, you become the group owner. Otherwise, you are the client. The server thread and client thread classes will be explained now. Sorry. OK. First is the group owner side. Create a server socket with any port number. Any number will do. The next is the most important part. The server side that called server socket accept will block until the other party connects. When the other party completes the connection, the gate opens and you get your lovely input stream and output stream. Next is the client side. The code is very similar. The client side can find the owner's address based on the P2P info we received earlier. The port must match that of the owner. These connect call blocks as well. Once the connection is established, you can proceed with it. See? Have you noticed this? Up to this point, both the server and the client get old-fashioned input stream and output stream. Everyone has used this to read and write files for college assignments, right? Let's try to write to this stream. Here we open a binary file and transfer the content as is. The more interesting part is the part reads, I mean the client. With socket programming, you do not know when the other party is going to write to you. Therefore, you basically wait for the other party to write something in an infinite loop, like this. Here, input stream read blocks. It will wait here permanently until they write something. Here, what the other party has written is transferred to the internal thread as is. Tips. Here's a tip. There is no such thing as boundary in TCP streams. Suppose you had written something twice. There is no guarantee that it will reach one by one to the other person. To keep the socket open and communicating, you need to define some protocol. For example, the payload length could be recorded in the first few bytes. This is just an example. Here, the first 4 bytes are content length, and the next 2 bytes are the delimiter. This is just an example, and you do not. It doesn't mean that that such a protocol is recommended. Just an example. The receiving side follows the same protocol to restore the information, which means read the first 4 bytes, then the next 2 bytes in order. Here we could make sure that the colon is restored properly for the delimiter, I mean. Now that we have defined a protocol, we cannot just read it as we have done in the past. Here, the file is delivered into several chunks based on the file size and buffer size, and receive them in order. Just to confirm, you do not need to understand this right here at all. Just refer to the source code later. Once you know what you're doing, then you can read the complete source code later. So don't worry, just focus on what I talked. Summary, most importantly, Wi-Fi Direct is simply a TCP socket once the connection is established. And what we take here with TCP sockets directly applies here as well. OK, next is Bluetooth. Let's speed things up. Bluetooth is main follower model. It could be more simply described as server-client model. Bluetooth Classic allows one main to communicate with up to 7 followers. Bluetooth uses communication agreements called profiles. For example, there are dedicated profiles for use with headsets, as well as profiles for use with health devices. Several other profiles are also supported in the Android framework. However, I will not talk about that today. What I will talk is about L2 cap and RF COM. L2 cap is a layer that, like the data link layer in OSI reference model. Then on top of that, RF COM was defined, which has a TCP-like retransmission functionality. Why do I talk about that? Because this is used extensively in Android Bluetooth API for sending and receiving general messages. OK, let's look at the code now. First, permissions. Android 12 adds a lot of fine-grained permissions, but don't worry about that. Just copy and paste. Next, we obtain an adapter to communicate via Bluetooth and check if Bluetooth is enabled on this device. Sorry. What we do here is similar to what we did with Wi-Fi earlier. We define a broadcast receiver for when we get information about connection partner. In the same way, bind to a lifecycle. Next, the client side makes itself discoverable. Only during duration can it be discovered freely by the other party. Now let's find discoverable peers from the client side by calling start discovery method. Now the server side tries to become ready for clients to connect to it at any time. To do so, the server uses the RF COM mechanism to obtain the Bluetooth server socket. Then wait and accept. We know we've seen that somewhere before. Yes, just like what we did with Wi-Fi. Accept blocks as we expected and waits for the client to connect. Next is the client. The client already has a list of peers to which it can connect, thanks to the broadcast receiver we just created. Once you have declared which peer to connect to, start the client thread via connect. What we are doing here is creating a Bluetooth socket via RF COM from that device info. This is how the client knows who to connect to. And the same again. Block with connect and wait for the connection to be established with the other party. From there, oh my goodness, it's our input stream and output stream. Everything else is the same as Wi-Fi. Summary, we found that Wi-Fi and Bluetooth Classic connect to other counterparts in a very similar manner, just in a slightly different way. So when you should use Wi-Fi, and when should you use Bluetooth? Well, you'll find that out at the end of this talk. So let's keep going. Last, BLE. BLE is also a server-client model similar to classic Bluetooth. In BLE in particular, the server is called the peripheral, and the client is called the central. BLE does not have a 7 nodes limit like Bluetooth Classic. Connections can be made as many as the hardware allows. BLE also has some concepts that Bluetooth Classic does not have. For example, BLE allows advertisement packets to include a small payload. This is utilized in iBeacon, for example. BLE uses a mechanism called GATT, G-A-T-T, to communicate after the connection is established. This is explained in the next section. Let's get this straight, because this is very hard to understand. GATT defines how peripherals and central talk to each other in BLE. Peripherals are, in simple terms, sensor devices. Peripherals have 1 or 2 more devices. A service is function provided by a peripheral. One service has 1 or more characteristics. This is a property of the service. I know this is very hard to understand, so I drew the diagram. Here, the peripheral, which means a sensor device, is a thermometer, which is described as blue rectangle. And thermometer have the service of delivering temperature information. This is the green part. And there is naturally some information about the temperature itself in that. The first yellow one is a characteristic that has the temperature, I mean the number. Here in this case, value 28 means 28 Celsius, excuse me. Now interestingly, there is also a characteristic to turn on the echo mode from the phone, the bottom half. If you write the value, for example, 1 to it, let's say the thermometer will be in echo mode. Are you getting the idea? This is how GATT service works. I explain this because understanding this concept is extremely important to understand the code itself. Otherwise, just looking at the code is very hard to understand. So what does this mean for Android? Starting with Android 4.3, Android devices can be a central. Starting with Android 5.0, Android devices can also be peripherals. What's the point of doing that? It sure depends on your ideas. Because, becoming a central is very natural, right? So you have the sensor devices, and you want to connect with the sensor devices with your Android, which is very natural. This is the central role. And on the other hand, the peripheral is Android device itself becomes a sensor device. Right now, there is no point for doing that. But it depends on your idea. OK, let's get started. Let me explain the scenario I'm about to describe. Here, 2 Android devices exchange text in both directions using BLE. This is expressed in BLE as shown in the figure. So the left-hand side means central, and the right-hand side means peripheral. And only in peripherals, those service and characteristics that I explained earlier is written. And it has a value, last message, and also has property, write and notify, which I'm going to explain from now. When a message is sent from central to a peripheral, it is written directly using BLE write operation. Conversely, when a peripheral sends a message to central, it notifies information to the characteristics that central is interested in. OK, it's time to check the code. First is the permission. Oh, sorry. Permissions are exactly the same as Bluetooth Classic. Here, too, is the same pattern. We are making necessary preparations for communication down the road. OK, things are getting complicated. We will start with an easy-to-understand explanation from central. Again, central is your PC or phone, which connects to the sensor device. Central scans the surrounding area for peripherals that can be connected by start scan. Same as before, when device is found, it is notified back. Let's keep the list. This list is the sensor devices around you. Once you find the device you want, specify it and connect. In the function, the GATT connection is initiated using that device information. And this is a callback after connecting to the GATT. This is huge. Therefore, let me focus on only a few that are necessary. The first one is on-connection state change callback. Once the connection status changes, you start to discover the service to which you can connect. In this case, this service is provided by sensor device. Once the service is found, look for a characteristic or descriptor in it. Descriptors are additional information. Don't worry too much about that. The information obtained is saved for later use. Remember, this is the connection. This is a callback where the connection is established. So all the information you need is given to you here. Here, Central enables notify for specific characteristics of the peripheral. This is a request for peripheral to spontaneously notify Central of any changes to these characteristics. So do you remember the diagram I drew? So the Central connects to the peripheral, which is the thermometer. And Central is interested in the value of temperature. So there are two ways. Sorry, this is not a script, excuse me. But one way is from the Central to query to the peripheral about the temperature periodically. That's one approach, but it doesn't scale. To address this situation, there is property called notify. So in this case, Central says that I'm interested in this temperature value, and please notify this. Then the peripheral sensor device is going to spontaneously notify it whenever the value changes. So this is a very useful feature. So here I'm going to do that. And this is the last step. The notify request made earlier will be notified to on-characteristic changed callback. This means that if you save a value here, you receive notification. Again, I said I'm interested in the temperature, and whenever temperature changes, it's notified through this on-characteristic changed callback. So if you need that, you need to save that. OK, the next step is to check the peripheral steps. The first step is to start the most important GATT server. Next, start an advertisement and make them available for connection from Central. Starting the GATT server means defining all the services and characteristics just described in that diagram I drew. Central connects to this. So you do not memorize it at all. Here, everything is defined just described in the diagram I drew. No need to know about the detail of this either. The GATT server is set up and just described in the diagram. Once everything is set up, start the GATT server and register the service so that the Central can connect to. Again, the GATT server also has a huge callbacks. Let's check only the important ones. First is the connection. When you connect with Central, you can get information about the connection peer. So let's save it. Next, we will fulfill some important duties as a GATT server. Occasionally, Central will throw out a request with a reply request. These requests must be checked correctly and replied to before communication can continue. Here, the response needed flag indicates that it's necessary. So whenever this is true, you need to respond back to the Central, excuse me. Same here. If the response needed flag is true, reply appropriately. In addition, on-characteristic write request comes to a request to writer characteristics. This means that the message was sent by Central to the peripheral. Therefore, we should add code to store this. The GAT server is now ready. All the remaining is to advertise. Here we adjust the power and frequency of advertisement. Now that you're ready, start advertising so that the Central can find this peripheral. This is what the advertisement could look like. Very simple. If it's successfully started, it's success. And likewise. Now we are ready. Let's try to do two-way communication with BLE. We will now implement this write method. As you can see, the process is divided into central and peripheral. This is because, as explained earlier, in the architecture, the means of sending data is very different. From central to peripheral, central just try to write it directly. On the other hand, peripheral needs to the only way from peripheral to notify data is through notify. We start with peripherals. Let's recall the process. Peripherals were to notify central of any changes in the characteristic to which it subscribed. In other words, when you want to send some message from peripheral, simply write a value to it and notify it. Now it is central. Let's recall this one as well. Central could write directly to the peripheral's characteristics, and it would be done. Now we've accomplished two-way communication. If you do not understand something, please take a look at the source code later, or reach out to me. Tips. I have not included something important at this point. This is too big a piece of data to send in one go. Sorry, if a data is too big to send in one chunk, what should we do? These problems did not occur with Wi-Fi or Bluetooth Classic. This is because they are streams. Remember those two output streams and input streams. There are several approaches to address this with BLE. The first is to extend the MTU, which stands for maximum transfer unit, with which you can transfer at once, to increase the amount of data sent at one time. The next approach is to send the data in chunks, even if it cannot be sent at once. Both approaches are discussed here. The first approach is to extend the MTU. Requests to extend MTU are very simple. Central can request an extension for peripheral with request MTU method and receive the result from on MTU change callback. However, it is not guaranteed at all whether the request will be accepted by the peripheral or not. So, from here, let's look at the way to handle the message larger than the MTU. Let's start with central. Making write requests from central to peripheral is fairly simple. Now, what happens if the message was bigger than the MTU size? If you are writing from central to peripheral, the Android framework will automatically split it up into several messages and send them to the peripheral one by one on your behalf. It's peripheral side that has to collect the chunks to the message and make it back to the original state. Let's check how to do that. There is a parameter named prepared write in one of the parameters of onCharacteristic write request callback. If that flag was true, your message was split and sent in chunks. In other words, as long as this is true, we need to keep collecting them and concatenate them at last. To do that, let's create byte array out of stream instance and keep writing the current chunk to it. After all the chunks were sent, except the very last one, peripheral will receive the on-execute write callback. This is a perfect timing to concatenate all the chunks held within byte array out of stream to restore the original state of the message. Next, we will see how we can handle the message larger than the MTU from peripheral side. Remember, the way to send message from peripheral to central is through notification. The bad news is peripheral does not have the mechanism to automatically split the outgoing message into chunks. What happens is notification simply ignores the rest of the message that is larger than MTU. So we need to split it and send them one by one manually. MTU varies depending on the device, but about 20 to 23 bytes seems the minimum, and 120 bytes is the maximum. So we need to write code flexible enough to let MTU value change dynamically. Although we decide to split messages by ourselves, we don't have a useful callback like Central does. So let's define a protocol to keep track of the total message size and current chunk number. Here, the first 1 byte is the total number of chunks. And the next 1 byte is the current index of the total chunk. For the rest are the payload. Next, we need to have the flexibility of changing the MTU dynamically. The initial MTU is 20 bytes. That value will be updated when Central makes an update request and accepted. This is a function that tries to send a message by splitting it to fit in the MTU. Again, we do not have to understand it now. It's just trying to divide them messages, smaller messages, and put the total chunk number and current index to each chunk as header. Once the message is divided into chunks, peripheral tries to update the characteristics with each chunk value and notify it one by one. This is the Central's code that receives the notification. For the chunk, remove the first 2 bytes, which are the header of the chunk. Then keep storing the payload part to byte array upstream so that we can concatenate it at last. If the chunk number and current index matches, it's time to combine everything together. OK, we are all done. Before moving on to the next topic, let me tell you the most important tip of BLE. When dealing with BLE operations, such as read, write, and notify, it's very important to make sure that every single operation is done sequentially. What it means is, for example, if you write to the characteristic, you need to wait until the on-characteristic write is called back before moving to the next operation. If you break this principle, you would most likely get the notorious GAT error 133, which basically means unknown errors. Sometimes people recommend putting retries and or sleeps to mitigate this error, but this is not a real solution. What we need to do is just to make sure every operation is done sequentially, or returning proper responses that is documented to do so. That's it. All right, so we have only 5 minutes left. Then let me go to the last section. How do we use each one differently? So the question is very simple. When should Wi-Fi be used? What about Bluetooth and BLE? Let's look at one by one. The first question, when should Wi-Fi Direct be used? The answer is when you need to send and receive big files. I conducted a small experiment in which I sent and received 1 megabyte file each other. It depends on the device and the distance between the 2 devices, but as you can see, Wi-Fi Direct is by far a lot faster than Bluetooth Classic. Now you may be wondering how fast is BLE. It's practically below 20 kilobytes and really unstable. So Wi-Fi is the only choice here. I also have small data. This diagram is a packet reachability rate over different distances. The higher the bar, the higher success rate. Wi-Fi showed slightly higher packet reachability at any distance. So if you are in a situation where you want to increase packet reachability at longer distances, you should probably go with Wi-Fi. Next, when to use Bluetooth Classic? The answer is any situations other than sending large files. Let me explain. First of all, researchers show that the Bluetooth's frequency hopping is more resistant to the network congestion. If you have to do communication at congested places, Bluetooth is the choice. Plus, I observed the pairing speed of Bluetooth devices are by far faster and stable than doing so in Wi-Fi Direct. Wi-Fi sometimes takes more than 10 seconds to pair. I also have some experiment result here. This is a packet arrival speed of various wireless communication means at different distances. The lower the bar, the smaller the arrival time is. At short to mid-range communication, Bluetooth Classic showed quicker packet arrival time. Lastly, when should we use BLE? I have no idea. I can't really think of a good reason to, at this particular moment, to use BLE, especially at peripheral mode, just for two-way communications. BLE is meant for communications between phones and sensor devices after all. But who knows? We may be able to come up with a brilliant way of utilizing BLE. I want to hear your idea. All right, this is the last topic, and this is real quick. I'd like to introduce Nearby Connection API to you all. For this 1 hour, I talked about various wireless communication methods in detail, but using this API will let you take advantage of even easier way to utilizing these communication ways. In short, if you use this API, I'm talking about Nearby Connection API, Wi-Fi or Bluetooth would be chosen properly under the hood by you just following the unified way that it provides. It can send bytes, it can send files, it supports multiple network topologies depending on your demand. It's pretty cool. Once you're familiar with each wireless communication way after watching my slide, you can try this out as well. OK, maybe I talked too much. Sorry about that. Do you have any questions? I think I have 3 minutes left. I'll be available throughout DroidKaigi, so do not hesitate to reach out to me if you have any questions. I will be sitting over there after this talk. If you have any questions, thoughts, and suggestions. That's it. Thank you very much.